Rate laws allow us to compare the rate of chemical reactions to concentrations of reactants. In other words, if you have a certain amount of concentration of reactant, then you can predict or calculate the rate of that reaction. Also, if you want a desired rate of a reaction, in other words, you want a chemical reaction to occur at a certain speed, then you can predict or also calculate the amount of concentrations you need to achieve that rate. So the rate law has this form, where the rate is equal to the rate constant, K, times the concentration of the reactant. In this case, the reactant is dinitrogen tetroxide. And that's raised to some power. We call that the order. Now in this problem, we're given the rate constant K. It tells us the rate constant is that, so we're given that. And we're also given the order because it tells us is first order. And that's with respect to the only reactant, dinitrogen tetroxide. So all we need to do is plug in these numbers to get the answers. Let's do part A in this color. So the rate is going to equal 6.08 times 10 to the negative 4 per second, or seconds to the negative 1. And we're going to multiply that by the concentration given is 0.200 moles per liter, which can be written molar. Let's plug these numbers in. 6.08 times 10 to the negative 4 times 0.2. So we need three significant figures. The rate is equal to 1.22 times 10 to the negative 4. And the units, none of them are canceled out. So it's molar per second. Right, and that makes sense because we're asked to find the speed or the rate of this reaction, and that's concentration over time. Now let's do part B. The setup is the same. We're given the rate constant, K, that's 6.08 times 10 to the negative 4 per second. This time I'll write it a different way, so you get different looks. All right, so that's K. Now the concentration of the only reactant I have is given to us as well. That's 0.319 moles per liter. So I'll write this a different way as well. So the rate is 1.94 times 10 to the negative 4 moles per liter seconds. So let's see if these answers make sense. This is a first order reaction. We're told that. What that means is if we increase the concentration of the reactant, we should see an increase in the rate. And that also aligns with the collision theory. The greater concentration of a chemical we add, the more they're likely to collide and increase the speed of that reaction. So between problems A and B, we're increasing the concentration of the only reactant we have, and therefore that should be proportional to the rate, and the rate did go up.